insane engineering of SpaceX Raptor engine and their evolution. SpaceX Raptor engine ramp up to something exceptional in the rocket industry. What is most shocking is that SpaceX chose to combine the second stage Starship with two distinct types of Raptor engines. One is the main Raptor engine, and the other is the Raptor vacuum engine. According to SpaceX, they chose to combine these two distinct types of engines since empty space is less in density and not as thick as Earth's atmosphere. As a result, the thrust required to push the second stage spacecraft through the space environment will be minimal. That is a different story than what is expected from the Earth's atmosphere, which SpaceX understands. In order for the second stage Starship to be able to transport cargo and some other scientific equipment for the Super Heavy to transport, it will need to have as much thrust as possible to overcome gravitational pull and still lift the entire vessel into space. Today, in this video, we will reveal the several types of Raptor engines that might be used to increase the thrust, which is also required to launch the entire huge Starship into space along with the cargo. This is Tech Space. If you're new here, we especially invite you to join many of our lovely fans. Kindly subscribe and click on the notification bell. It motivates us to produce more fantastic content like this, and you'll have a lifetime access to all of our high-end tech videos. Since SpaceX was established in 2002, the company has produced 4 families of rocket engines: Merlin, Kestrel, Draco, and Super Draco, and they are now developing another rocket engine, Raptor, as well as a new line of Methox thrusters beyond 2020. As of 2012, each of these engines produced has been designed for initial use in SpaceX launch vehicles, especially the Falcon 1, Falcon 9, and Falcon Heavy, or the Dragon capsule. Then the main engine fuel was kerosene-based, using RP1 and liquid oxygen (LOX) as the oxidizer, whilst the RCS control thruster engines used storable hypergolic propellants. SpaceX has also built 2 kerosene-based engines through 2013, the Merlin 1 and Kestrel, and has publicly discussed a much larger concept engine with high-level design named Merlin 2. Merlin 1 powered the first stage of the Falcon 1 launch vehicle, and is used on both the first and second stages of the Falcon 9 and Falcon Heavy launch vehicles. The tungsten water-moderated nuclear rocket employed a regeneratively cooled nozzle. This type of nozzle, which uses hydrogen as a coolant, provides a technique for cooling the walls. It also preheats the hydrogen to fulfill the heat exchanger and topping turbine needs of the rocket system. The ablatively cooled carbon fiber composite nozzle was used in the Merlin 1A and the Merlin 1B. The Merlin 1A, which produced 340 kilonewtons of thrust, powered the first stage of the first 2 Falcon 1 flights in 2007. The Merlin 1B featured a slightly more powerful turbopump and produced higher thrust, but it was never flown prior to SpaceX's switch to the Merlin 1C. The Merlin 1C was the first in the series to include a regeneratively cooled nozzle and combustion chamber. It was initially fired with a complete mission duty firing in 2007, flew on the 3rd Falcon 1 mission in August 2008, propelled the first privately developed liquid-fueled rocket to safely achieve orbit, and later powered the first 5 Falcon 9 missions from 2010 to 2013. Methalox engines came into the picture in November 2012, when SpaceX CEO Elon Musk revealed a new strategy for the company's propulsion side, creating methane or Methalox rocket engines. SpaceX's research on Methalox engines is only for the company's Mars technology development program. They have no intentions to develop a Methalox-powered upper stage engine for the Falcon 9 or Falcon Heavy. Now let's get to know about some questions that are very important. Why is SpaceX using methane? Since SpaceX is focused on reusability technologies for their rocket lines, when traditional rocket-grade kerosene burns, it creates residue, a process known as coking. Methane fuel burns cleaner, resulting in less residue buildup, allowing engines to be reused more frequently without needing to be serviced. Raptor has a regenerative cooling system, which routes clean methane fuel from the turbine via the engine chamber and nozzle heat exchangers before it reaches the preburner and turbine. Both propellant components are totally in the gas phase by the time they reach the engine injector. How much fuel is burned per second by a Raptor engine? The booster's 31 Raptor engines provide 212 GW of power. Musk's 380 ISP Raptor would need a 3.3 M nozzle. One Raptor engine is expected to use 565 kg of fuel each second. And since 1 kilogram equals a litre, then it means the Raptor engine burns 565 litres of methane fuel per second. Thomas Mueller is a rocket engineer and a rocket engine designer from the United States. He was a founding member of a Hawthorne, California-based American aerospace manufacturing and space transportation corporation. He is most recognized for his work on the TR-106 and SpaceX rocket engines as an engineer, and regarded as one of the world's greatest specialists in spacecraft propulsion, and possesses multiple US patents for propulsion technologies. So, he is the guy behind the design and working principle of SpaceX's Raptor engine. For orbital ascent, the booster fires all of its multi-engine out-capability engines at the same time. The boost stack maneuver appears to utilize half of the core's engines, but the atmospheric entry, burn, and landing appear to use only the inner cluster. According to SpaceX, the Raptor production process will use a significant amount of additive manufacturing, or you can also call it 3D printing, a technique that has recently been brought to the engine's structural development and demonstrated on SpaceX's Merlin engine. Because 3D printing allows creation of lighter parts that would not be achievable using traditional methods, it provides significant cost savings and improves the thrust-to-weight ratio of the engine. Another advantage of 3D printing engine components is the speed of which design changes can be implemented in new components, allowing the engine design to go through several iterations in a short time span, rather than spending weeks and months recasting components based on updated specifications. Now let's take a look at the various specifications of SpaceX's Raptor engine. First is the sea-level version, or SL. The Raptor SL has a nozzle ratio of 40, resulting in a nozzle diameter of 1.7 meters, and an expansion tailored for operation in the observable atmosphere, since the booster will only work at heights of slightly more than 100 kilometers. According to a basic calculation, the baseline Raptor SL has a vacuum thrust of 3,297 kilonewtons. Calculations also produce a propellant flow rate of 931 kilograms per second at a mixture ratio of 3.8, while tank capacities on the ITS vehicles indicate a mix closer to 3.7. Raptor, like the Merlin 1D series, can handle exceptionally deep throttling, with stable combustion feasible as low as 20% of the engine's rated thrust. This allows the ITS booster to ascend actively and still throttle its engines on the way back to a propulsive landing, which requires active management of the vehicle's thrust-to-weight ratio. Another one is the Raptor VAC. SpaceX's release of Raptor adheres to the company's fundamental design philosophy of simplicity through commonality. Instead of constructing a whole new engine for the rocket's upper stage, the company adapts the Raptor for optimal performance in a vacuum by equipping it with a bigger nozzle engine known as VAC. This allows the Raptor VAC engine to leverage the same turbopump, piping, and chamber components, reducing development costs and time. Raptor VAC is designed to have an operating thrust of 3,500 kilonewtons, with a specific impulse of around 382 seconds. The VAC engine's expanded nozzle has an area ratio of 200, requiring a nozzle diameter of roughly 4 meters. VAC version is used on the ITS spacecraft and tanker, both of which are outfitted with 6 VAC engines plus 3 sea-level engines for the tanker's propulsive landing back on Earth and the spaceship's daring retropulsion and landing maneuver on Mars, as well as the ascent to begin the homebound journey. According to the theoretical spaceship's design, only the 3 SL Raptors at the middle of the vehicle are capable of gimbaling for precise attitude control during ascending and landing maneuvers. During maneuvering in space, differential throttling of the outer VAC engines is employed to control the whole Starship. Now, the final type of engine SpaceX has introduced is the full-flow staged combustion cycle. The full-flow engine design offers several advantages over staged combustion engines. These advantages include increased performance, reliability, and reuse considerations. Higher performance is obtained by introducing propellant into the combustion chamber in a gaseous state, and that triggers a faster reaction. The usage of separate turbines for the fuel and oxidizer turbopump decreases total turbine power when compared to a single-shaft turbopump system, with a single turbine driving both pumps. Having the entire propellant flow pass through the turbines also helps to cool them and creates a manageable thermal environment. The full flow method also produces a more friendly environment for the engine piping than previous designs. extending the life of the power units and allowing them to be reused on several flights. Now over to you, mention the 3 types of Raptor engines SpaceX has developed to lift off the Starship into space. Please do well to share your thoughts in the comment section below. Until next time, please like, share, subscribe, and whilst you're still around, why don't you click on one of those flashing videos on the screen for more content.